In the previous lecture, we learned that for buck converter, its voltage conversion ratio is equals to D. So you might ask, will the voltage conversion ratio still be equals to D in DCM mode? In the previous section, we learned that the DCM mode, we have the inductor current small ripple approximation no longer valid. So what kind of difference will it bring to the analysis of DCM operation? So in this section, we will try to derive the DCM mode voltage conversion ratio for the buck example. So first, we plot the key waveforms for the inductor current waveform and diode current waveform of the buck converter. So I put it in the right corner here. So in the time domain, we put the waveforms of IL and ID, which are the inductor current and the diode current. So we learned that there are 3 operation modes in DCM. One is from 0 to D1 TS. So in operation mode 1, the inductor current rises linearly to the peak value. So this is denoted as the peak. And diode current equals to 0. Then in mode 2, the switch is off, diode is on. So the current begins to drop linearly. So mode 2 happens from D1 TS to D1 plus D2 TS. The diode current will be equals to the inductor current. And in mode 3, both MOSFET and the diodes are off. Mode 3 happens from D1 plus D2 TS to TS. So the current of inductor equals to 0 and the diode equals to 0. That is a complete period of the DCM operation. So we know that this is mode 1. This is mode 2. And this is mode 3. So also the peak current can be calculated by the current slope times the duration of mode 1. So we can have the I peak equals to the slope is Vg minus V over L. Duration equals to D1 TS. So this is the peak inductor current equation. And also we can denote this average inductor current as equals to V over R, which is the average load current. Okay. Then we try to analyze the mode 1, mode 2, and mode 3 separately. First, let's look at what happens in mode 1. So we already know that mode 1 occurs from 0 to D1 TS. We can plot the equivalent circuit of buck converter in mode 1. Here is the input source. The switch is on. Q is on, right? Which connects the input source and the low-pass filter network. So here is L, here is C, and here is the load resistance R. There are several quantities we need to mark, right? One is the output voltage, and one is the inductor current as IL. Also, the inductor voltage is critical here as VL. And we care about the capacitor current as IC. So in mode 1, we can express the inductor voltage and the capacitor current accordingly. So we will see that the inductor voltage, VLT, can be analyzed by KVL principle. So this equals to input voltage minus output voltage. And IC T can be analyzed based on the KCL analysis in this node, so which equals to IL T minus the load resistance. Based on small ripple approximation, this equals to V over R. Next, let's look at what happens in operation mode 2. Mode 2 happens from D1 TS to D1 plus D2 TS. In mode 2, the Q is off, diode is on, so we can also plot the equivalent circuit accordingly. So the diode is conducting, which shorts the input of the low-pass filter network. So here is the output voltage, inductor current, inductor voltage, capacitor current. So the diode is right here. So this is the diode current. We can write those equations for the mode 2 accordingly. So in mode 2, we'll have inductor voltage equals to minus output voltage, since this voltage is 0. And the capacitor current still equals to ICT minus V over R, because this part is unchanged with the mode 1. Next, let's look at in operation mode 3. Mode 3 occurs from D1 plus D2 TS to TS. And also we can plot the equivalent circuit. In mode 2, both the MOSFET and diode are off. So we'll have a kind of open circuit here. So here's L, C, and R. Output voltage, inductor current, IL, inductor voltage, VL, capacitor current, IL. So we can again write those use those two expressions. inductor voltage in mode 2 equals to 0 because there's no current flowing into it. So the di over dt is 0, so the voltage is 0. And capacitor current still equals to subtraction of IL. And load current. But this time, the IL equals to 0, right? So where equals to 0 in mode 3. Okay, so that's the expression for inductor voltage and capacitor current in all the 3 operation modes. Next, we can apply the principles we learned, like volt-second balance. For the inductor, so we know that at steady state, the average inductor voltage equals to 0. And the average value can be expressed by mode 1, mode 2, and mode 3 times their proportion accordingly, right? So this will be equals to D1 times the value for mode 1 plus D2 counts D2 parts, mode 2 counts D2 parts times this value plus 0 in mode 3. This quantity at steady state should be equal to 0. So based on this equation, we can derive that the output voltage can be expressed by the input voltage times D1 divided by D1 plus D2. So furthermore, we can express D1 plus D2 by the input-output voltage, right? So equals to D1 over output voltage divided by input voltage. So here happens to be the voltage conversion ratio for DCM. So this equals to D1 over voltage conversion ratio, M. And next, we try to apply the charge balance for capacitor. Capacitor charge balance tells us at steady state the average capacitor current equals to 0. The capacitor current expression is relatively simple, and they are unified as inductor current minus load current. So this means that the average inductor current minus average load current equals to 0. So we can express the average inductor current accordingly. So this quantity equals to average load current. And regarding the average inductor current, we can again analyze based on the waveform of average of the inductor current. If you look at this triangle waveform, the average value should be equals to the integral of inductor current over one switching period divided by the length of the switching period equals to 1 over Ts times the integral from 0 to Ts times inductor current dt. So interestingly is that this integral equals to the area of this triangle. The triangle area equals to the base times height divided by 2. So the base is equals to d1 plus d2 ts. The height is right, I peak, divided by 2. For the I peak, we learned that it's equals to this quantity, right? So we insert this 2 I peak here. And also, the d1 plus d2 equals to d1 over m. So we can replace d1 plus d2 by d1 over m. So this will be equals to I peak d1 over 2m. So this part is gone. Then I peak equals to this quantity. So equals to input voltage minus output voltage. d1 times d1 is d1 square ts over 2lm. Okay, so now let's erase the left-hand side of the whiteboard. Okay, we have erased the blackboard. So you can see that for inductor average current, so this is expression. Based on charge balance of capacitor, the inductor average current equals to average load current. So we write this equation to the left-hand side. So we have Vg minus V times d1 square Ts over 2Lm equals to V over R. So we can modify based on this expression. So this is equivalent to that we extract the V here, right? So if we extract V, then this will be 1 over M minus 1 d1 square Ts. And the V are cancelled on both sides. So the left-hand side will have 1 here. And here we have like 2Lm. So those two expressions, they are equivalent. So based on the right-hand side equation, we can rewrite it, right? Rewrite it. So by putting M together, right? So we can see that the 1 over R equals to d1 square Ts over 2L. So the M terms are placed together. We will have 1 over M square minus 1 over M. So this is like a quadrant equation for M, right? So we can solve M based on the high school math. It's like a parabolic function, a parabolic function. So M will have 2 roots, but 1 root will be abandoned. We only keep the positive roots because the voltage conversion ratio is positive. So we can have the expression of M equals to 2 over 1 plus square root 1 plus the fraction of 8L and RTS D1 square. So that's the feasible route for the voltage conversion ratio. Since we have introduced the K parameter, right? K, as we can remember, K equals to 2L over RTS, which can be found here. So we can replace this part by K to further simplify the expression. So we'll have M equals 2. In DCM, we'll have this 2 over 1 plus square root 1 plus 4K over D1 square. For this continuous conduction mode, the condition for this is K is smaller than K critical. For Bach, this equals to D prime. And another part will be the CCM mode. We learned that for CCM mode, the voltage conversion ratio equals to D, which we denote as D1 here, right? For CCM. So where K is bigger than K critical equals to D prime. Till now, we have fully solved the voltage conversion ratio for Bach in DCM. Next, we can graphically plot the voltage gain versus the duty ratio and see what we can obtain. So basically, the M is a function of duty ratio D1. And the y-axis is voltage conversion ratio, which is a function of duty ratio and K. So D exists from 0 to 1. So here is 0.5. Suppose the circuit is in DCM. Then we'll have a straight line. So voltage conversion ratio equals to D, right? Means here is 1. And if the K drops to be lower than critical, then we will enter into DCM, right? But it's not that all the whole range the circuit is in DCM. Most probably for this area, since D will be small, so the circuit still work in CCM in this region. So we'll have such a behavior. So this is the case for K equals to 0.5. Right? For K equals to 0.5, if D is bigger than 0.5, the circuit return to the CCM. But for this region, it is DCM, so follows this function. And if we further decrease K, we'll have such a profile. For K equals to 0.1. So we'll have the circuit operate in DCM from 0 to 0.9, okay? And even further, like the K equals to 0.01, for majority of the region, the circuit will be in DCM. Okay, so we can see that the DCM introduced the non-ideality in the pulse width modulation. In this subsection, we have learned the voltage conversion ratio of the DCM buck converter. So as we analyzed, the voltage conversion ratio will be affected by the inductance, switching period, load resistance, and also by the duty ratio.